So what we have to go over to start class then is what oxidation numbers are. An oxidation number is kind of unusual. But if we get past the kind of weirdness of it and simplify it, it helps us determine what we have to go over today, which is whether or not something was oxidized or reduced. An oxidation number is technically a hypothetical number. It's a number we give to either an atom or an ion. And the point of that number is to suggest how many electrons are around either that atom or ion. You've actually been using oxidation numbers this year when you've been working with ionic compounds, because the charge of an ion is its oxidation number. Unfortunately, not only ionic compounds have oxidation numbers, but covalent ones do as well, and that's where things get a little more unclear for a Chem 1 student. Wait about 30 more seconds and we'll move on to the next slide. Interesting.
So where's this number put in relation to like an element?
So that's what we'll go over that in the next couple slides.
Okay. So
we will need to give elements or ions oxidation numbers. That's the skill that we have to learn today. Yeah. Okay. Second slide, why are we figuring this out? A lot of the reactions that we've already done this year are oxidation reduction reactions. I don't know if you actually have to write down a lot of this, by the way, and that first bullet point I don't think is that important. What we are going to do today, towards the end of class, is we are going to determine if a reaction is an oxidation and reduction reaction. Really, in my mind, the only bullet point that you should write down is the last one. Let me get the little part here out of the way. This last bullet point is what I would suggest you write down. The first two is just more of me talking points. Last bullet point. Today we have to learn how to assign oxidation numbers. So elements or ions in a compound, we have to give them a number that kind of designates how many electrons do they have around them. If we do that for every element or ion in a chemical reaction, we can then identify which things lost electrons, which things gained electrons. Which, if you're not familiar, that little E with the minus sign that my cursor is pointing to right now, that's the abbreviation for electrons. And if something loses electrons, we'll be able to identify it as being oxidized. If something gains electrons, we can be able to identify it as something that was reduced. Again, in Chem 1, in this advanced reactions unit, we are just touching upon some of the topics that we need to go over within chemistry. Redox chemistry, because oxidation reduction is just called redox for short, has a lot of applications. It's just that we don't have time in the Chem 1 schedule to go over all those applications. For example, Ben in the back of the room is doing the last lab for AP Chem this year. The second half of his lab, he's going to create a battery. Batteries are oxidation reduction reactions. Cellular aspiration was on your last unit test. That's an oxidation reduction reaction. So there's a lot of reactions within our world that are based upon this. Again, we can go over a little bit of it here or there, but really we need to make sure you understand how to identify these parts instead. Now, oxidation numbers are on your periodic table. Again, I don't think you have to actually write down this slide. At the beginning of the year, I told students, if you look at those tiny little numbers directly above a symbol, so for example, for oxygen, there's a tiny -2 and a -1. These are the oxidation numbers for oxygen, the most common ones. And within there, the bold one is the most common one. If I look at the periodic table up on the wall, and I look at something like copper, there's a 2 and a 1 above it. Well, first semester, when we taught you naming, we said that 2 and the 1, those are the two possible charges for copper. Copper can be a +2, copper can be a +1. That hasn't changed. Technically, those are also oxidation numbers. So with metals, like iron, a 3 and a 2 and a 6, copper is a 2 and a 1, nickel's a 2 and a 3. With metals, their oxidation number is the same as their ionic charge. So we're actually not asking you anything new when it comes to that. The tricky part is nonmetals. Oxygen is a -2 when it's in an ionic compound. And yet both on the periodic table I'm pointing at its wall and the one on the smartboard, it says -1 is another possible oxidation number. Our goal with the first part of class here today is to go over how to assign oxidation numbers. If you treat them like charges, even though sometimes it's not really a charge, it's technically an oxidation number, but if you treat it like a charge, it usually isn't that overwhelming. So my last slide, which I don't think we have to write anything down, is addressing the fact that on the way in, you picked up a sheet that says rules for assigning oxidation numbers. Let's get that sheet out, please. So what I'm going to do is I'm going to read through those 8 rules on this sheet. And then we're going to do a couple sample problems together to see if we can, in fact, do goal number 1 for today, which is identify oxidation numbers. So rule number 1 for oxidation numbers says the oxidation number of any free or uncombined element, including diatomics, is 0. Oxidation number for monoatomic ions is their charge. So notice for example number 2, Fe +2, well, +2 is its oxidation number. And that's not meant to be anything tricky there, but if things have a charge, their charge is their oxidation number. Rule number 3, all the alkali metals, which is in group number 1, they have a +1 oxidation number. Group number 2, the alkaline earth metals, is a +2, aluminum is a +3. Fluorine is always a -1, is oxidation rule number 4. Hydrogen's a +1 unless it's bonded to a metal, which is rule number 5. Rule number 6 talks about how oxygen is usually a -2, although there's 2 unusual instances for oxygen that we try to avoid in this class. Number 7 is a rule that we try to avoid as well, but might pop up. In binary compounds, the more electronegative element has the oxidation number equal to its charge. Really, number 8 is the important one. The sum of all the oxidation numbers of a compound should equal 0, unless that compound has a charge. So if you notice on the bottom, there's a bullet point for 2 compounds. The first one is KClO3. What I want us to do right now is assign oxidation numbers. So if we look at our periodic table, in other words, get out your periodic table. Let's look directly above K, potassium, on our periodic table. How many little numbers are directly above potassium? Just 1. And what is that number? +1. In other words, the oxidation number for potassium is +1. Again, that's not meant to confuse you. That's actually meant to be what it is. Let's look above chlorine. How many possible oxidation numbers are there for chlorine when you look above it? 4? There's a fair amount of them. So you know what I'm going to say about chlorine right now? Let's skip it and move on to oxygen. Now oxygen I showed on that slide. Oxygen's either a -2 or a -1. For you guys, by and large, you can right away assume that oxygen's a -2 for an oxidation number. So again, what we do is we look at our periodic table. There's only one option for potassium. I know potassium's oxidation number. It's a +1. Oxygen is almost always a -2, especially in Chem 1. We try to keep it simple. So -2 is that one. We have to figure out the chlorine oxidation number as well. This is where Rule 8 on that Rules for Assigning Oxidation Numbers worksheet you picked up on the way in tells us the oxidation numbers of the entire compound have to equal out to 0. So they all have to equal out to 0. Here's how I would figure out the oxidation number for chlorine. There's 1 potassium in the formula KClO3. So I have an oxidation number of 1 there. The chlorine I'm trying to figure out, so that's kind of my variable. I could call it X if I wanted to. There are 3 oxygens. If each oxygen is a -2, that means my total negative is -6. So I multiply -2 times 3 to get to the -6 part. Are we okay with that? Combining all the oxidation numbers of something that is neutral should give me 0 overall. So now, a little bit of algebra. What must be the oxidation number of chlorine in order to get that to balance out? +5. There's a way to check to see if we're right. Is +5 one of the options on your periodic table? Mm-hmm. Good. If you had a number that wasn't on there, either I wrote a bad problem, which is possible, because we're simplifying things and it gets a little more complicated, so I might have just wrote a problem that wasn't good, or you made an error with the math. But if I asked you a question of assigning oxidation numbers for each element in KClO3, K is a +1, Cl is a +5, O is a -2. They're not really charges, but we can think of it as charges balancing out. So questions on that first one? Second one's a little bit trickier. I want to do that one with you as well, and then they're going to give you a chance to practice this. Second one gives you ammonium nitrate, NH4NO3. Is there any elements in this formula that we could right away write down its oxidation number for?
Hydrogen and oxygen.
Hydrogen's what?
Hydrogen's
Hydrogen's a +1. The only time hydrogen isn't a +1 is if it's bonded to a metal. That was rule number 5. So Hudson saw that there's no metals in here, so he knew hydrogen was a +1. And then oxygen's almost always -2. Is there several options for nitrogen? Yeah. And that's what makes this a little tricky, is there's several options for nitrogen. Does anything stand out when you look at the formula of NH4NO3? There's 4 elements there. What does that mean? I mean, I didn't call it nitrogen tetrahydrogen nitrogen trioxide, because what's NH4? Ammonium. It's a polyatomic ion, right? NO3, that's a polyatomic ion, nitrate. What I would do to solve this problem is I'd almost break it into 2 parts. Here's the ammonium polyatomic ion. Here's the nitrate polyatomic ion. Hudson already said hydrogen's a +1. And I have 4 of them. So if I kind of multiply 1 times 4, that means the hydrogen supply a total of +4 for that oxidation number. Nitrogen's what I'm trying to find out. So N plus 4, or how about N plus a +4? In the previous problem, I had the compound equal out to 0 because it was a neutral compound. Is ammonium polyatomic ion neutral? No, it's a +1 charge. So in this case, I'm going to have it all equal out to +1. What must the nitrogen be in ammonium? Let's do the math here. N plus a positive 4 equals a positive 1. What must N be? Nope.
Negative 3.
Negative 3. Is negative 3 one of the options on the periodic table for nitrogen? Yeah, so we're good. By the way, if you didn't realize I should set it equal to plus 1, you set it equal to 0 instead. You would add your nitrogen to be a negative 4, and I'm pretty sure negative 4 isn't an option on there, so that's another indicator that that would be the case. Let's look at the NO3. We already knew oxygen was a minus 2. Minus 2 times 3 gives us a total of negative 6 for the 3 oxygens. So nitrogen plus that negative 6 should equal the charge of the ion, which is a minus 1. What must be the oxidation number for nitrogen then? Plus 5. So our first goal of the day is to identify oxidation numbers. Now, someone would look at this, and I know this one was tricky because I gave you polyatomic ions, but I did that on purpose. I wanted to give you a hard one as well. Someone would look at this and say, wait a minute, nitrogen's a minus 3 in ammonium, and it's a plus 5 in nitrate. How can the same element have more than one oxidation number? Oxidation numbers are a way to represent how things are bonded. And quite frankly, the bonding that nitrogen has in ammonium is different than the bonding that it has in nitrate. And because of it, it has different numbers. Now, we could go back and show you Lewis dot drawings from first semester, and I could then relate it to that, but you guys probably don't want to do that. I just saw the look on Allie's face, and it was a, oh, I don't want to do that type thing. So, you either have a neutral compound, and you look to see, like K is a plus 1, I knew that one already, oxygen's a minus 2, let's figure out the Cl minus, or the Cl part of it. Or you have polyatomic ions, and we can figure that out as well. What I'd like you to do was you picked up a sheet with a 1 through 9 on it. How about you have that out reactions? So what we just worked on was assigning oxidation numbers. And that skill is a must when we start applying it to chemical reactions. And that's what the second half of the class is going to be for now, is we're going to write out an entire reaction. We're going to assign oxidation numbers for everything, and then we're going to figure out what was oxidized, what was reduced. That labeling is a very common thing for chemistry students to be able to do. So, within oxidation reduction reactions, or redox reactions, something is going to be oxidized. So there's going to be an oxidation equation. I have two definitions of what oxidation is. The first definition is the current definition. The second definition is the original, way back when they first discovered this and thought of this definition. The reason why I show you that last bullet point will come clearer when I go over what is reduced. What you want to know is that first dashed definition. Oxidation reactions refer to something losing electrons. Now again, long time ago, really didn't know about tracking electrons from one element to another in a chemical reaction. So long time ago, they noticed reactions in which something gained an oxygen. It started without an oxygen, then it bonded to an oxygen. That's why they call it oxidized. That's where the name came from. Reduction reaction. I know it seems weird right now, but a reduction reaction is when an element gains electrons. This is where students are like, but wait a minute, to reduce means you have less of something, so shouldn't that be the other way around? No, for two reasons. One of which is the old original definition, that last bullet point on here. Originally, when they came up with this idea of oxidation reduction reactions, they noticed that in some reactions, something was originally bonded to oxygen and then it wasn't. It reduced the oxygens that it was connected to. That's kind of where the term reduction came from. Oxidation came from gaining oxygen. Reduction came from losing oxygen. You're reducing the oxygen bonds. You'll see in a little bit, however, that these two terms, oxidation and reduction, work well with the numbers that we figured out as well. Because in reduction, your oxidation number gets reduced from the start to the end of the reaction. In oxidation, the oxidation number gets bigger. It becomes more oxidized from the start to the finish. So, the dashed points. Not the bullet points after, but the dashed points are the ones that you need to be aware of. I only show the bullet point version just to give you an idea of where did these terms come from. You need to, for lack of a better term, memorize oxidation is losing electrons, reduction is gaining electrons. Because you will be asked on your last unit test, and then probably in your semester exam as well, to identify what was oxidized and what was reduced, or to identify what gained electrons and what lost electrons. So, to help you, I'm going to give you a gift. And it's one of those few gifts I give you all year that you may remember 5 years from now. Kind of like if I bump into you in the hallway, Eliza, and I ask you what's new, you're going to say C over lambda. You're not going to tell me about your day because new is one of the variables in the light equation when we did light math first semester. I actually ran into a girl that I student taught. So I student taught back in the early 2000s. And a couple years later, I bumped into her in the streets of Madison, and she asked me what's new. And I started talking about what I was doing, and she right away called me on it. It's like, no, you're supposed to answer C over lambda. That was the last time I got burned by that. I'm going to give you something just as memorable as that today. Are you ready? My gift to you is Leo goes Gur. Leo's a lion, lions go Gur, right? Lose electrons oxidized, gain electrons reduced. Leo goes Gur. The response isn't as enthusiastic as I would have expected because this is amazing, folks. By the way, just to get it out of the way, there is a second mnemonic device to know this. It's far inferior to Leo goes Gur. Leo goes Gur is great. Because sometimes I can just be looking at Jack's paper and I'll just say, Gur, right to him. And he'll know, oh, gain electrons reduced. Okay, I see what I did wrong. There's a second mnemonic device that's sometimes used, sometimes taught, sometimes in textbooks, called oil ring. Oxidation is losing, reduction is gaining. That's okay, it's not telling you what you're gaining or losing. And quite frankly, oil rigs are not good for the environment because combustion reactions CO2. So I prefer to go with lions. Who doesn't like to look at the lions in the zoo and hear them roar? Here is an important part to finish this second slide. In an oxidation-reduction reaction, you are always going to have something losing electrons, so being oxidized, and something gaining electrons, being reduced. You can't have in a chemical reaction something gaining electrons without something losing them as well. It's almost like a conservation of mass idea. Something gains, something loses. So the reason why we call them redox reactions is the two parts go together every time. If you ever find yourself trying to do some of these homework problems and you end up not having something oxidized, but something was reduced, you did something wrong. Just like when you check your oxidation numbers on the periodic table and it's not on there, you did something wrong. Remember, I will put the audio notes that I'm recording too online if you ever needed to look at this again. Okay. Don't know if we have to write this down. So this is more of just me talking. You don't have to worry about writing down. What we need to do now is combine what we started with class of assigning oxidation numbers with these definitions for Leo goes GER. So, my first bullet point here says, you guys know how to assign oxidation numbers. We're going to do that for an entire chemical reaction here today. So everything in that chemical reaction, we're going to write little numbers up above. Because we're going to keep track of what thing gained electrons and what thing lost electrons. Because, second bullet point says, if we look at the oxidation numbers before and after in a chemical reaction, we can tell something was reduced because its oxidation number gets smaller. Or if it was oxidized, the oxidation number got bigger. And my last bullet point on this slide says, a reaction is a redox reaction if there's a change in oxidation numbers. Bless you. Not every type of reaction is a redox reaction, ladies and gentlemen. So keep that in mind as well. A lot of them are, and you're going to see that as we go along. What I want to do is give you an example problem. So how about you write this reaction in your notebook right now? After you write this reaction, actually this was the exact reaction that Ben was doing in the back lab bench just a little while ago. I want you to take a minute right now to assign oxidation numbers for everything in that reaction. So I'm going to stop talking, give you a minute to write those little numbers above everything. But if the SO4 is the same start to finish, it doesn't actually react or change at all. Rule number one, elements that stand by themselves, like the zinc on the reactant side and the copper on the product side, if they stand alone, what's their oxidation number? 0, right? Since sulfate is a -2 polyatomic ion, the Cu on the reactant side must be a, what oxidation number? +2. Same thing goes for the zinc then over there. So here's the change that I noticed. Zinc started as a 0 and it became a +2. Because in ZnSO4, it's in a compound, it's going to have an oxidation number. Copper starts as a +2. After all, the compound's called copper 2 sulfate. It became a 0. What we have to remember is electrons are negative particles. And if you lose a negative, you become more positive. Which is why zinc lost electrons. If you lose electrons, you're oxidized. Leo. Copper, on the other hand, gained electrons. And if you gain electrons, you're reduced. GER. Most students have an easy time with the assigning of oxidation numbers. But then it's the, okay, I have to label which one was oxidized, which one's reduced, and they forget the rule. So there's two ways you can look at it. Again, an electron is a negative particle. Zinc must be losing negatives to become positive. On the other hand, copper is becoming less positive over time. So you could look at it that way. Or, the last way, instead of Leo goes GER, if the oxidation number is reduced, if it goes down, that thing was reduced. If the oxidation number goes up, that thing was oxidized. So either remembering that electrons are negative and Leo goes GER can help you in that identification, or my bottom point here, when oxidation numbers go down start to finish, Plus 2 is bigger than 0. That number goes down. It was reduced. If oxidation numbers go up, 0 to plus 2 means the number is increasing. It's becoming more oxidized. Our entire goal of today is to get to this point where you're going to write a balanced equation and then you're going to assign oxidation numbers to determine in that reaction what was oxidized and what was reduced. Next class, we just practice it some more. So if we don't get it today, we're going to get more repetition next time. If you get it today, heck, you just got to keep doing what you're doing then. What